reconnection with some old friends and some new people. I'll be talking about synchronization of clocks as a core theme. And, I will explain to you why I have to speak about it. And I will make statements and assertions. Each of those assertions will be proved because the proofs are simple. And I request the students to look at it attentively so that these proofs which I present here has importance for theories of fundamental physics, theories of relativity, theories of dynamics. Okay. So when you talk about time, the first question is, what exactly is physical time? What do you mean by physical time? Usually we just draw a space-time diagram. We are quite used to that, with an arrow going up like that to represent time. But if you really think about our familiarity with time, physical time, you will realize that it is impossible to define and use the notion of physical time in space without matter. Space without any matter, there is no time. In other words, time presupposes matter. In fact, if you look closely, you will realize that time is synonymous with the dynamics of matter. I will not go into explanations of this at present. A very detailed treatment of physical time is in my recent book called Gravity's Time, published last year. So today, the theme is not about time. It's about having assumed that there are precision clocks capable of measuring time, what we call time, how to deal with the relativity of time. Now, when I say time is dynamics of matter, what I mean is, in every case where we use time in physics, what we are doing is to compare the dynamics of one chunk of matter with the dynamics of with another dynamics. It's always a comparison of dynamics, what we call time in a differential equation. It's just a comparison of matter, incremental comparisons of matter compared to another dynamics of another piece of matter. For example, this is as good a clock as any other clock, for example. No, I like this kind of clock. It has been also used in certain contexts. Now, one thing which is very important in the usage of time in physics is its property. Physical time is local. A clock here with an observer O at X, even time at X. It has nothing to do with the time at X prime with an observer O prime. To link them, you have to have a messenger signal between these two. So time is a very local kind of a concept. And so this kind of a messenger signal is always required when you want to talk about everybody's time. Otherwise, time is my time, your time. It's all completely separate. We don't normally notice this messenger signal. When you look at these two clocks, for example, you think they are synchronized to some extent. But that is why light coming to you from the clock, two separate signals are coming. You are only comparing those two separate signals. So it is subtle. And this is the whole basis of relativity of time, this comparison of clocks at different points. That needs messenger signals. So when you ask the next question, not ask it, what is time, but what time is it? It's a common and universal question, yet it's very difficult and subtle question for physics. And we try to answer this. No, so this question is actually an elementary synchronization call. Essentially, when you ask what time is it, some signal has to pass between two observers. And we need to fix a precision with which this question needs to be answered. That's our choice in some sense. Always we don't need to know it very precisely, but in some cases we need to know it precisely. So that is why clock precision becomes very important when you ask this question. What has been achieved in the precision of marking time and its synchronization across space is really remarkable in the last half a century, I would say. In fact, the factor by which we improved our clocks and the accuracy of synchronization, it's really mind-boggling, big factor. We had this clock rotating Earth. It's one of a kind, but universal, which we have been using, and its precision is very, very high actually. Massive Earth rotating angular momentum is reasonably constant, it has fluctuations, but its precision can be of the order of better than 10⁻⁻⁻, even better for a long time. Then of course in the 1920s, from pendulum clocks, we had pendulum clocks in between, I have not shown here. We had this quartz oscillators, which changed the measurement of the style at which we measure this variable time. But then in the 1950s, big revolution happened. We chose atoms as a standard of frequency and the clocks based on that. And here there were a lot of detailed lectures, so I don't have to talk about that. Here I have shown NPL's clock. It was built a few years ago. So this era, after 2000, is an era of optical clocks. Again, sudden increase in the precision by orders of magnitude. Now, as you all know now, atom in an atomic clock is a frequency reference. It is not an oscillator. Oscillator is still a mechanical oscillator, but it's a reference for frequency, which is very stable. And this picture has been shown before here by Subhashish. Louis Essen, who pioneered the cesium beam clock in NBL, UK. And similar activities were also developed in the US around the same time. Louis Essen learned some of this technique from there. He is a very decorated scientist in UK. He was till he published a little book, few pages, said special theory of relativity, a critical analysis. Within another 2 years, he was excommunicated from science scene. He was a decorated, he is behind our definition of a second in terms of atoms. He is behind our definition of a meter in terms of wavelength. He is behind all this. And he was excommunicated, he couldn't publish after that. But that's his story of history. I don't want to go into. This happens this has happened to Galileo. This happened to Louis Essen. This happens now. This will happen tomorrow also. That is because we are just human beings. We are doing physics, but we are also just human beings. Now, if you look at the progress which happened in the last 20 years or so, frequency comparison, not comparing clocks, but just comparing laser frequencies across distances. There has been very remarkable developments. For example, this is a European network, which is operational, where you can compare frequencies across countries. with a fractional accuracy, which is in the 10 minus 20, 10 minus 21, which is amazing. Comparing frequencies across countries using optical fiber network, which is standard commercial networks. You don't need very special things. It is frequency comparison. So this is kind of way today we can compare frequencies across laboratories. When you come to clock comparison, here there was already talked by a group of people. You can see that again, clocks, different clocks, either in the same laboratory or different laboratories are being measured. The same laboratory, when it's measured, if they are compared, the accuracies are exceeded 10 minus 80. So this is all very remarkable. Because in fact, if you make this kind of clock, you cannot even use it for regular application because it's so precise that you don't know how to use it except for very specialized application. Now there is another thing which comes from astronomy, which is not yet part of our regular marking of time, but it's a pulsar astronomy. As you know, millisecond pulsar are very heavy neutron stars, which are recycled after some accretion and so on. They have rotational frequencies of periods of tens of milliseconds and very stable. How stable? There are pulsars with the fractional stability, long-term stabilities of its period is changing only by 1 part in 10 to the 19 per second. So they are comparable to laboratory clocks in certain ways. The short-term accuracy is not that great, but even that is sub-microsecond. So this is another set of array of clocks in the sky. You need radio telescopes to access them, but these are all part of our timing network. But these are all separated clocks. Each clock is a separated clock. To link them, you need light signals, electromagnetic signals. So that we come back to this clock, this question about synchronizing. And even for, yesterday this was mentioned, GPS to receiver, again there is a electromagnetic signal. Otherwise, there is no connection between these two times. How to synchronize two clocks? The answer to this fundamental question is not unique. In fact, at present, the global synchronization of time is based on a consistent convention that is agreed on consensus. Why I am saying this, I will explain this. There are two ways you can think of to synchronize two clocks. One is you send a signal and get it back. Now, the up signal and the down signal, these two clocks are fixed in a frame. The frame could be moving, like the Earth is moving through the universe and so on, which we cannot know because it is a principle of relativity that's a uniform motion cannot be detected. But there could be some movement. And there is no guarantee that this delta t and delta t prime is the same. Even though the distance between these two clocks in the frame, these two clocks, that is fixed. Another way of comparing synchronizing two clocks is to synchronize two clocks at one point here and then move one of those clocks to the other clock and resynchronize there. That's another method you can think of. It is tedious, it is expensive, but that's a legitimate method of synchronizing two clocks. But of course, what is popular is, of course, sending a light signal. Now, you can see that, therefore, synchronizing two clocks, nature of propagation of light, motional time dilation, and even gravitational time dilation comes into picture. When you compare these two clocks, if there are few centimeters up and down, today, that introduces a gravitational time dilation which exceeds the precision of these two clocks. So, today's clocks, few centimeters, already they are out of synchronization, gravitational. If gravitational time dilation is 1 part in 10 to the 16. This is our 1 part in 10 to the 18. And so the interplay between time, propagation of light, motion, gravity, all this have to be taken care of when you talk about synchronization. Now, Poincare, who was chairman of the committee for global synchronization of time in around 1900 in France, because BIPM, Bureau Standards, is in Paris. So he studied synchronization of global synchronization, and he has written a lot about it. I quote from this: I suppose that observers placed in different points set their watches by means of optical signals, that they try to correct the signals by the transmission time, but that unaware of their translational motion and thus believing that the signals travel at the same speed in both directions, they content themselves with crossing the observation by sending one signal from A to B and another from B to A. The point is, he makes it really very clear that we have to just believe the two signals, because we don't know that we are moving and we don't know what the law of propagation of light is. So there is an assumption which is involved here. And we can assume that delta T up is same as delta T down if we can consistently carry out this process without internal contradictions. That's all we can do. Because of the principle of relativity, that inertial motion cannot be detected. So therefore, inertially moving frames are equivalent to frames at rest. So Poincare synchronization, the key assumption is a convention by consensus. And it's not a physical fact that T up is same as T down. Now, Einstein's synchronization, it came after special relativity was introduced, so it is another few years. There's a postulate that the relative velocity of light is a constant and isotropic, independent of any movement of velocity of the frame of the two clocks. So the frame might be moving, but it's irrelevant in the theory. Therefore, by postulate, it is asserted that delta F is same as the delta T down. The two timescales are now equal. So that is Einstein synchronization. When the other process, by shifting the clock, if you do synchronization, the difference between these two, I just want to point out. When you transport a clock, you have to ask the question, what happens to time in a clock that is moving? You need a theory. What speed should I use to calculate the changes in rate of the clock? So there may be velocity dependent changes like time dilation, but what velocity can I use? Do I use the velocity of transport in the frame, or I also add the velocity of the frame? You have to have a theory for answering all these questions. So the only verifiable synchronization that independent of any theory is when clocks are synchronized at the same spatial point. Two clocks are nearby as possible. You can synchronize them without referring to any theory. Okay. This is a very important point. Now, in clocks in Einstein's special relativity, you know, if you transport a clock relative to another clock which is deemed at rest frame, there's a time dilation. The approximate formula here. This is a standard thing. So the clock in the reference frame, by definition, has zero velocity, rest frame, in the special theory of relativity. But in any picture of relativity, like the old Poincare Lorentz relativity, which is set up in ether, there it is a velocity relative to the ether, absolute single unique frame, where that velocity is what you have to take. So these are different theories dealing with the synchronization of time in different ways. Now, in all this, if you ask the question, clock when you say clock, it's a physical device, it uses matter, properties of matter, dynamics of matter. Why does a relatively moving clock run slower? There is no answer in current physics. Nobody can answer that question. Why does a relatively moving run slower? What's the reason? What's the physical reason? Because there is a physical clock, there's some physical process going on. One would have expected a physical process can be affected only by a physical interaction. A Hamiltonian being written for an interaction and so on. Nothing is there. But we know that moving clocks go slower.
Let us say that the two clocks, different clocks, having same velocity. Will you have some time difference?
In the present theory, no. They have the same time dilation, whether it's a pendulum clock or an atomic clock. Which is a remarkable fact. And if you ask the reason, it can only point to equations. Now, the second question is actually slightly different from the first question. Why does a moving clock run slower? I'm not talking anymore about relative movement, but something kind of absolute movement. So these are all questions which I'm not going to answer here. Answers are there in the book for all these questions, but that is not the theme today. For example, in this clock transport synchronization, there could be two things. One is, you can say dilated time is 1 minus v square by 2c square. V is the local velocity of this transport. And then I correct for that if I want, or do a slow transport so that it is insignificant. But it could be a different formula where I consider the motion of the whole frame itself moving through the universe. Then the time dilation formula is entirely different. There is 1 minus v square by 2c square. Then there is a u square by 2c square. And also there is a dot product u dot v by 2c square. Which is very significant because this is, when you multiply with this time, it is a term d dot u. D is a distance, dot u by c square. This is a very large correction. We don't know which one of this actually functions this. Okay. So the two clocks will have can have a synchronization gap, which is large, but we cannot verify this. To verify that, another signal has to come back. Then this term reverses sign, and there is no evidence remaining about our synchronization gap. So therefore, that is why the consensus become important. We just believe, we agree to synchronize using the Einstein's Poincare method. Now let's focus on only that kind of synchronization. Assume that the signal velocity is constant in both ways. An assumption, as I said. So therefore, a signal going to one of the distant clock takes the same time to come back. And I can just start a signal at some notional 0, takes time. When the signal comes here, I set the clock as 0 here. Then when it comes back, I know the total time which is taken, t, and I fix a midpoint as a synchronization point. This is Einstein-Poincare synchronization. So we can assume that these two clocks are synchronized without really knowing what the exact time the other is. By convention, we agree that this midpoint is where the two clocks are synchronized. However, if the relative velocity of light is not a constant, then its assumption of true synchronization is false. After all, the invariance of the relative velocity of light is just a hypothesis. I'm saying that there is not a single experiment in the last 100 years which proves that the relative velocity of light is a constant. I'll come back to this. Whereas in the Poincare picture, what is really happening is one way it is c minus v and another way it is c plus v, but we don't know what this v is because of the principle of relativity. But it's truly c minus v and c plus v, but the total time is still t. So the synchronization works, but the other clock could be with a synchronization gap d dot v by c square, which we will not never know. That's why I'm saying, so in one way, it is t, pt by, this is plus synchronization. When the signal comes back, it has a different sign. The total, this term cancels out. There is no evidence of what we committed. Therefore, we assume that we are innocent. Okay. So we assume that they are truly synchronized when they are not really synchronized. But it doesn't matter.
What is D here? Capital D?
Capital D is a distance between the
Perpendicular distance between these
two clocks. So, for example, here I have said between the UK National Physical Laboratory and the Delhi Laboratory, if there is absolute frame, the theory of relativity is based on absolute frame and not Einstein's special theory of relativity, this error or the synchronization gap would be about 2.2 microseconds. It is very large compared to the precision of clocks. That is just to give you a number. Anyway. No, I'm saying there are two possible kind of theories. Yeah, I'll come to this because, so since I made an assertion now that there is not a single experiment which proves that the relative velocity of light is a constant. However, since there is a general popular impression that the Michelson-Morley type of experiments prove that the relative velocity of light is a constant, and textbooks say so, I want to give you two proofs that any two-way experiment of the Michelson-Morley type, any, are incapable of deciding this question, what's the nature of propagation of light? The velocity is the ratio of distance traveled and the duration taken. It is a secondary quantity. It's not directly measured in this. The ratio between these delta x and delta t. And both have a second order, v square by c square correction in relativity because of Lorentz factor 1 minus v square by c square. But when you talk about relative velocity, this Lorentz factor cancels out, which is a ratio of delta x and delta t. Okay. Therefore, this kind of experiment can never address the question, what is the real one-way velocity of light? Because it's a first order, v by c effect. These experiments are sensitive only to second order terms. That is one proof, but one can prove this directly. For example, look at one of a Michelson interferometer or a cavity, any of those things. Assume explicitly that velocity of light is Galilean. That is, relative velocity is either c plus v or c minus v. We assume it explicitly. Then we know that the time to go and come back will be, one way it is L by C minus V, L is the distance. Another way, by going back, light going back is L by C plus V. So as you say, there is only a second order signal, 1 minus V square by C square. However, if both time dilation and end contraction are real physical effects, it will affect this time here, also the length here, and you get 2L by C as if the velocity of light is constant. So we have assumed that the velocity of light is Galilean. Even then, in a Michelson-Morley type 2-way experiment, you always get the result. This signal is not visible. The experiment is not capable of addressing this question. So whatever is.
I'm not able to understand how can I assume class.
No, for the light is coming back, it is Galilean. In one direction it is C minus V, the other direction is C plus V. Like a velocity of sound. So Michelson-Morley experiment, two-way experiment are consistent with both Galilean propagation and propagation with a constant relative velocity. It is consistent with Einstein's theory or the old either theory of Poincare and Lorentz. You cannot distinguish. Yeah, of course. Like a interferometer just set up in. So please for students, please do not carry around the unfounded belief that Michelson-Morley experiment is a proof of the constancy of relative velocity of light. There is no such proof from any experiment. L is the length of the interferometer. No, this is your rest frame. The interferometer is set up here. I'm sitting with the interferometer. One way it is a C plus. Yeah, of course. I mean, it is set up. Yeah, we can discuss this. Let's go ahead. So now I want to go back to this V by C effect, first order effect, which is what you will see in synchronization. So I started late. The concept of simultaneity is, I started 10 minutes late. This is from Einstein's book, Relativity is a Special and General Theory, where he explains the synchronization of time, simultaneity of time and time. So he gives an example. Lightning has struck at two places A and B, far distant from each other. I make the additional assertion that these two lightning flashes occurred simultaneously. If I ask you whether there is some sense in the sense in this statement, you will answer my question with a decided yes. But if I now approach you with this request to explain to me the sense of the statement more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. So as I said, this is a subtle question. Why? We require a definition of simultaneity such that this definition supplies it with a method by means of which one can decide by experiment whether or not both the lightning strokes occurred simultaneously. So what he has is, there's a platform, there is a train, there are two observers, one on platform, one on the train. They coincide at the midpoint when the lightning occurred. Then he's asking, if this is simultaneous for one observer, is it simultaneous for the other observer also? In his theory, he has to assume that the velocity, relative velocity of light is a constant. So we want to answer this question because it's a very, very important question. So we want to examine this. There are two frames. They are relatively moving with a velocity v. O and O prime are the two observers in the two frames. Lightning, two events have happened simultaneously when they coincided at the midpoint. The light comes through. So in the frame O, which is relatively moving, relative to O prime, in the relative velocity of light is a constant. The signals will arrive at the observer at equal times, at the same time, it is simultaneous. There is one thing I want to stress here. Whether it is light or sound, its relative velocity does not depend on the velocity of the emitter. It is true for all waves, not only for light. Velocity of sound, relative velocity of sound does not depend on the velocity of the source. The question is only whether relative velocity depends on the velocity of the observer. This is a very, very important point. It is normally not recognized. So in the frame of O, we said the midpoint, since the relative velocity of light from both points is equal, the events will appear as simultaneous. And in the frame of O prime, there also relative velocity of light is a constant. The velocity of the source doesn't, it is immaterial. So it does not matter. Once the event happens, light comes from two events with equal velocity. The redshift, the Doppler shift is an independent thing. It doesn't affect the velocity of a pulse, right? Yes. But the velocity of the pulse doesn't depend on the velocity of the emitter. The frequency of the pulse does depend on the velocity of the emitter. So we are not talking about. So what I'm saying is we have found the answer to the question which Einstein posed here. If you assume that the velocity of light is constant for all observers, these two situations, O and O prime, will see these two events simultaneously. Please think about it very, very hard and more than twice. However, so this is a conclusion. If the relative velocity of light is independent of the velocity of the source and the observer, two events that are simultaneous to one observer will be simultaneous also to another who is in relative motion. However, suppose the velocity of light was Galilean, c plus v and c minus v. Then in the frame of O, suppose it is simultaneous. But then in the frame of O prime, they have different velocities, c plus v and c minus v. Therefore, it will appear not simultaneous, but sequential. So its conclusion is very clear. The relative velocity of light is not an invariant constant. Two events that are simultaneous to one observer will not be simultaneous to another in inertial motion. It will be perceived successively. Now we have the answer. As I said, all of you should think about it and make sure that you understand this. This is a summary. In the frame of O, if it is simultaneous, in the frame of O prime, it is not simultaneous. Whereas the top figure shows, okay, let's not worry about that. Now, in the book as well as in his paper, Einstein concluded the following. Please go and check this. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. We thus arrive at the important result. Events which are simultaneous with respect to reference to embankment are not simultaneous with respect to the train and vice versa. What I'm saying is that he inadvertently used Galilean light to arrive at his conclusion. He made a fatal mistake in the treatment of simultaneity in his paper as well as in his book. You can go and check this fatal mistake he made in the formulation of special relativity. Anybody can go and read what he has written and check this. There's a reason for saying that. It is true that our experience is that if it is simultaneous for one observer, it is not simultaneous for the other observer. Because if two observers coincided at the middle when the two events happened, when the light arrives, these two observers are separated. So if it is simultaneous for one, it cannot be simultaneous for the other. What I'm saying is that the postulate that the relative velocity of light is a constant for all observers is not consistent internally. It's not consistent with experience. Now, in a short time, I want to say something related to all this. I want to give more proofs because I want to give you proofs for every assertion I make. You know that there is a GPS constellation. All of you have the mobile phone which uses this. A signal comes from a satellite. Mobile receiver takes it. The only information available to calculate distances is the time difference. There's a timing signal which comes. This is my position. This is my time. It comes to the receiver. Receiver takes that thing and supposed to use Einstein's relation that the distance is just simply constant relative velocity of light, which is c, multiplied by the time difference. So that is what is expected. The signal comes, there is a signal receiver which may be moving. There's a time difference between the satellite time and the observer time, that denote PR. Einstein's special theory of relativity, if used in GPS kind of navigational system, this is what you expect. The distance is given by just constancy multiplied by the time difference. This is what people think, popular perception about the GPS. But this is not the GPS algorithm. People who know how GPS works, this is not the algorithm which is used. The algorithm which is used is with a correction, this correction. What is that correction? It is added as an empirical correction because initial GPS satellites did not work the way it was intended. It was added later from experience. What is that correction? That correction corresponds to using, instead of C minus V. And the receiver is moving with velocity V. If it is C minus V, the magnitude of that is given by just this, which is essentially approximately this. So in a working GPS system today, what is used is Galilean light. Otherwise, this navigation will not work. You will be off the road in no time because this correction is very, very large, of the order of about 70 meters per second. Okay. So what I'm saying is what you carry as a light mobile phone in your pocket is a heavy burden of a wrong theory. It confirms Galilean propagation of light. So GPS operation itself falsifies Einstein's special theory of relativity. It's a drastic statement, but I can give you more proof. For example, I want to give one more proof and then stop. Suppose you consider a path for the light to propagate, or any wave to propagate, which is set up like this. There's a clock, waves are generated here, and it goes around in this path while the observer is moving inertially. Suppose you consider this kind of a situation. If you use sound will go around at its velocity. If you use light, in the same time, sound goes around once, light will go around 1,000,000 times. Now I want to consider a system where both are in propagation together. So one pulse of sound and one pulse of light is generated here simultaneously. Observer is moving, detector is moving. Light will go around 1,000,000 times, sound goes around once. They are detected also simultaneously. I arrange the experiment like that. So they are emitted simultaneously, detected simultaneously. So these are events which are universal for every observer. Both are together. So the ratio of round trip is some integer. Light goes around integer times and sound goes once. So therefore ratio is an integer. And therefore, since it's an integer, it should be the same integer for all observers because events are simultaneous. Emission is simultaneous, detection is also simultaneous. Let's calculate. So n is an invariant. For emission to detection, light takes, you can do this calculation, I will not explain this. You get the total time taken as this expression. For sound, it is once, so there is no n there. This is, but the sound velocity I am taking as s, light velocity is c. So that is by this expression. The ratio is c minus v by s minus. This you can calculate. However, in the moving frame, the detector frame, the same thing can be calculated. The total distance traveled is by sound is relative velocity of sound, which is s minus v, by some time. But the same time is taken for the 1,000,000 trips of the light. But if I assume that the relative velocity is c and not c minus v, this is the distance traveled. The ratio is this, which is not n. So therefore, again, I'm showing there's an internal inconsistency in special theory of relativity. If this kind of a simple configuration shows you the velocity, the inconsistency even without an experiment. But I have done direct experiment of measuring one-way relative velocity of light. The same thing happens. And since light hypothesis is inconsistent and incorrect, and therefore the theory is also slow. So I should stop now because I'm just exceeding time. You may not know this. Suppose I synchronize two clocks, really synchronize in the laboratory, let's say some laboratory, and move one of these clocks. And I ask you what happens to this time in the moving clock. All of you will say there is a time dilation, though I cannot compare this unless I bring back the signal from there. But at least theoretically, I can say there is time dilation. I can move this clock further. There is further time dilation, and I can keep on moving this clock. But since Earth is a globe, it will come back to me. It's a good thing. Now I can compare directly in the laboratory. And I can see whether there's a time dilation according to prediction. The surprise is that in this particular experiment, which I showed you, the transporter clock runs faster and not slower. Does anybody know this result? This is experimental result. It runs slow, not slower, but faster. Saying that the laboratory clock, which was at rest relative to me, it ran slower. It had a time dilation rather than the transporter clock. It had more time dilation rather than this. So therefore, what I'm saying is even that prediction, Einstein's prediction, goes wrong in many situations. Of course, the oldest experiment it showed was the Hafe eating, very famous experiment. Though they didn't report it this way. If you look at the data, this is the result. So I'm saying there are various evidences. I cannot go into that, but all this comes from synchronizing these precision clocks, the single problem of synchronization. And why does this happen? There's a reason why that theory is wrong. See, when special theory of relativity or other theories of relativity were constructed, we didn't know anything about cosmology. We didn't know what was the content, matter content of universe. In 1920, the known universe was just Milky Way and a few nebula and stars. That's all. It's only after Hubble's observations and result in 1929, extragalactic universe became part of our knowledge. We realized that the universe is at least 1,000 times larger with matter everywhere. So the background space of Einstein's theory or quantum mechanics, quantum field theory, is just empty space. Minkowski was with small gravitational correction. But the real, our only universe, the real universe is this. Our background space is with matter at critical density and its gravity everywhere. You can calculate the gravitational potential of all the matter in the universe in this room. Whether approximately or not, it's not important. You can calculate. It happens to be numerically equal to the square of the velocity of light. The gravitational potential of all the matter in the universe happens to be equal or close to the square of the velocity of light. It's a known thing. I will not go into all those calculations. So when you say a clock is moving, it is moving in the background space of all this matter and its gravity. So this is what is happening. Now a clock which is stationary in the presence of all this matter sees one gravitational potential. The clock which is actually moving in the presence of all this matter, it sees a slightly different gravitational potential. That difference is 1 minus v square by c square. That is a reason for time dilation. That's a reason for everything in relativity dynamics. What I'm saying is all relativistic effects and all dynamics, including Newton's law of motion, are consequence of the gravitational effects of all the matter in the universe on dynamics. So I stop here. So what I'm saying is, this is current theories. They are grossly incorrect. The correct theoretical basis is with that matter background. These are two different worlds and two different sciences. And this is our actual world, the real world. Einstein, when he wrote a paper on superconductivity, right after Kamerlingh-Onnes discovered it, he said the theoretical scientific researcher is not to be envied because nature, or more precisely put, experiment, is a merciless and not very kindly judge of his efforts. She never says yes to a theory. In the best case, merely perhaps. But in most cases, simply no. If an experimenter agrees with the theory, it means perhaps. If it does not agree, then it means no. Every theory is sure to experience its no someday. Most theories already do so soon after their formulation. Of course, he may not have expected his theory might face the same fate. Anyway, all this and much more, without exception, is discussed in this book, New Relativity in Gravitational Universe. Here, my intention was to just talk about precision clocks and their synchronization. But there are many more evidences which confirm what I'm saying. However, I also want to show this letter, which was written by Galileo to Kepler. My dear Kepler, I wish that we might laugh at the stupidity of the human herd. What do you have to say about the principal philosophers of this academy who are filled with the stubbornness of a serpent and do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth. These are great matters that they do not occasion any surprise. So evidence, even if it is given, acceptance of evidence is a social phenomenon, because we are human beings doing physics. But I give all the evidence in this book, and I have given you many evidence with proofs today, and I hope the situation will change. Thank you very much. Sorry for the extra time I took.
We are already over time, so if there is one or two pressing questions, or we can also discuss in the lunch period.
Like, people are trying to use this atomic clocks to detect dark matter. Will it affect for this?
No, see, I'm just saying that at present we have an observation of the universe. We don't know the nature of all that matter. We know so 5% maybe is normal matter. There is some dark matter which is gravitationally measured. There is some unknown matter also like that. We don't know all this, but we know that the universe seems to be consistent with the fact that there is the average matter density of all this together is near the critical density. But what I'm saying, even if it is some of those matter is out of consideration, even when 5% of matter is there, let's take the 5% of matter. It has its gravitational potential. It's only 5% of what I'm calculating here. But that would have given you a correction in a time dilation experiment amounting to 5% of the special relativity effect, which we don't see. So it's either full or none in this case.
That was an interesting talk. Thank you, Professor Unnikrishnan.
So I'm here tomorrow also. Anybody, please think about those proofs, because those proofs are genuine proofs without any, they are insurmountable proofs, I claim. So if you have a counter argument, you come up with that counter argument. Otherwise, you have no choice but to accept what I'm saying. Thank you.
And we thank all the other speakers also for this session. So this closes the session.